instructions here. Okay, CPS. Okay, change the processor state. Okay. So what is this CPS instruction? So this CPS instruction we had discussed on the three core mask register, interrupt mask registers, right? PRI mask, fault mask, as well as the base PRI. Do you remember that? PRI mask, base PRI, and the fault mask registers, right? So these three registers we can access using this instruction, the PRI mask register and the fault mask register using this CPS instruction. Okay, I'll just open the, just give me a minute. I open the manual. Cortex manual. Right, we had this the programming model, these three registers, PRI mask, fault mask, and base PRI. These are the three fault registers, three interrupt mask registers. We have this PRI mask and fault mask, which are very important mask registers, right? So PRI mask, if I come to this PRI mask register, or it is a 1-bit register, right? So in this register, if we write 1, then it will mask all the interrupts except reset, NMI, and the hard fault. Only 3 interrupts will be active. All other interrupts will be inactive, right? So this is the PRI mask or the priority mask register. So now I want to write 1 here to mask all the interrupts. How do I do that? Okay, so to do that, I have to use this instruction called as, I'll go to the instruction set here. Okay, I'll go to the CPSID instruction. Okay, so CPS stands for change processor state. Okay, so what is the CPS IDI? Means what it will do is D stands for disable. Okay, I stands for PRI mask register. Means it will operate on the PRI mask register, right? So when we use this CPSIDI, disable all the interrupts. Okay, means it will mask all the interrupts except reset, NMI, and the hard fault. Only these 3 interrupts will be active. Okay, what are the interrupts? Reset, NMI, that is the non-maskable interrupt, and the hard fault. Only these 3 things will be active. Okay, all other interrupts, these 3 things will be enabled. Okay, all other interrupts. Okay, so whatever other interrupts are there, they will be disabled. Okay, so if we use this instruction, so what it will do, how it will do, it will set the PRI mask register. Okay, it's a 1-bit register. It will set the PRI mask register. So same way, if we use the CPSIE, E means it is enable. D means disable. Disable the interrupts, enable the interrupts. CPSIE I stands for PRI mask. Okay, so CPSIE I means it will clear the PRI mask register, means it will enable all the interrupts, whatever was disabled here. This is to enable and this is to disable the interrupts. Okay, so next, what we will do is this clear? Yes. Okay. Can you please type Bo on the chat? Yeah. Okay. What does PRI mask do? Okay. Okay. Yeah. Got it. See, this is the PRI mask registers. We have the core registers, right? These are the various uh, core registers present in the CPU, in the ARM Cortex CPU. We had discussed this earlier, right? Do you remember? R0 to R12 are the general purpose registers. R13 is the stack pointer. We have two stack pointers, process stack pointer and the main stack pointer. This stack pointer is used to hold the address of the top of the stack, address of the topmost element of the stack. If this is my stack, you know what is a stack, right? The stack is nothing but it is lasting first out data structure, right? So some part of the memory of the microcontroller, if this is my microcontroller memory, then a part of the microcontroller memory, we are going to use it as a stack. If this is my stack, okay, this is the stack memory, right? So we will be pushing the uh, data into the stack, right? And we are going to pop the data out of the stack, right? This is the stack data structure. We know, right? Yes, Bo? Okay. Yeah, I'll come to this PRI mask. Okay. So whatever is the topmost element of the stack, okay, if this is the topmost element, then whatever is this address, right? This address will be stored in this stack pointer. Okay, whatever is this address. Through this stack pointer, you are going to access this stack. Similarly, we have the link register, which will hold the return address from the function or subroutine. Okay, if this is my function, so this is the calling function main. Okay, from here, I will call a function, for example, add function I'm going to call. Right? This is my add function. When I call the add function, it will go to the function, and after completing this function, it will come back to the next instruction. after the add instruction call, right? So after this add function call, it has to return this address, whatever is the return address from where it has to return back to the calling program. This address is stored in this link register. Okay, the return address from the function call or the subroutine is stored in this link register, right? Similarly, PC will hold the address of the next instruction to be executed, right? So, apart from these things, we have the process status register, which will hold all the different flags, what we discussed, negative, zero, carry. Then we have the overflow flag, saturation flag. These are the various flags. The ISR number, it will store currently active interrupt service routine number, interrupt continuable instructions, if then structure, right? T always has to be equal to 1, this bit, right? These things we had discussed earlier. This is our program status register. Next, coming to the PRI mask. Okay, so if we come to PRI mask, what does this do? This PRI mask is a 1-bit register. Okay, this is our priority mask register. Okay, this is a 1-bit register. It consists of just only 1 bit, the 0th bit. Okay, this is a interrupt mask register. Okay, so you know different interrupts are present in the microcontroller, right? If I open the microcontroller reference manual, okay, so this is 429 NICE reference manual. These are the various interrupts that are present in this microcontroller. There are around, how many interrupts are there? There are around 88 here. In the 429 microcontroller, there are around 90 different interrupts are there. Okay. Suppose if the CPU is doing some critical work. Okay. So when you are doing some critical work, you are focusing on doing, if somebody comes and disturbs you, right? So it is the disturbance to your work, right? So if it is some critical work which you have to deliver, so what you will do, you will switch off your phone. I assume you will switch off your phone. You will just whatever, close the door so that no disturbance is there, right? So till you complete your critical work. Is that true? So switch off the TV, switch off the mobile phone, switch off all your notifications, close the door, right? Till you complete your work, right? Yes or no? Yes? Will you do that when you're doing some exams preparation, or while you're doing the some online exam you're giving, something like that, right? So you will focus and do. Similarly, if the CPU is doing some critical work, right? Interrupt is nothing but the disturbance to that, right? So it is doing some work. If other peripheral comes and asks you, asks the CPU, okay, you please do my work. The CPU is not in a position. It has to complete that work. What it has to do, it has to uh, disable that, just like how you disable or your notifications in your mobile, or you close the door like that. It has to disable that disturbance from the peripherals, right? For that, it will mask all the interrupts. Okay, so that it will not get disturbed while doing the critical work. Right, understood? So CPU will disable all the interrupts.
Critical.
Okay, except some very critical interrupts.
Critical
Right,
work.
very critical interrupts it will enable. All other non-critical interrupts it will disable. So what it will do is, if we are using this PRI mask register, okay, so if we are using this PRI mask register, then very important interrupts are there, like reset, non-maskable interrupt, and the hard fault interrupts, which will take care of the critical functionalities of the CPU. Right? Only these three interrupts are enabled if you are making use of PRI mask register. If I make this as 1, right, then by default, all these interrupts are enabled. Okay, by default, when you switch on the processor, all the interrupts will be enabled. Okay, so in the core, all the interrupts will be enabled in the core. Okay, whatever is in the core register, it will be enabled. PRI mask will be equal to 0. Okay, if I come here, you can see that these are the system registers. PRI mask value is 0. So if PRI mask is 0, then all these different interrupts, whatever 90 interrupts I've shown now, everything is enabled in the system, in the core, right? So if the CPU wants to do some critical work, it will disable the interrupts. Okay, except the critical interrupts. What are those critical interrupts? Reset is a very critical interrupt. When you reset, the system has to be reset, right? It has to start from the beginning. It has to load and start from the beginning. Next is the non-maskable interrupt. Means always this interrupt will be enabled. Means, for example, clock security system or some power down happens, the register contents should be properly backed up, right? So some critical functionality, we will be using this non-maskable interrupt. And if any faults occur, that will be handled by this hard fault interrupt. Right? For example, in the critical task, what you are doing, some instruction is not defined. Usage fault is there. There is a bus error. Bus fault is there, right? And memory error is there. Memory fault is there. To handle those things, hard fault interrupt is used. These are the three very critical interrupts, right? So when you make this PRI mask is equal to 1, what it will do is, it will enable reset, NMI, hard fault. Okay, and these all other interrupts will be disabled. Okay, just like, for example, you are doing some critical work. Okay, so very important notifications. For example, you are expecting some notification from your university. What you do is, you will just enable the notifications from the university, right? That is the critical thing. All other notifications from your friends, that is the WhatsApp notification or whatever is your Instagram notification, all other notifications you are going to turn off, right? In the same way, very important interrupts you are going to turn on. all other whatever interrupts are there here, these things will be turned off. If I make this PRI mask is equal to 1, right? If I make this as 0, it is just like you are enabling all the notifications from all the different sources, WhatsApp, Instagram account, or whatever X account, whatever accounts you have, all the notifications you are enabling so that everything is enabled in your system, right? When you make this PRI mask is equal to 1 means what you will going to do, you are going to enable or turn on only the critical notifications from the system. Okay, non-critical notifications, everything is turned off. It is disabled. That's the role of PRI mask. Right? Is it clear? Oh, what is the use of PRI mask register? Yes or no? Is it clear? Shall we move forward? Okay. So that is the purpose of PRI mask register. Now, how I will write 1 into this register? How I will write 0 into this register? I need to write, right? The user should write 1 and user should write 0. Right? User should write 1 or 0 into this register. So how to do that? Okay. To do that, these two instructions are available. That is CPSID and CPSIEI. Okay. I'll come here to the Cortex manual instruction set. This instruction. Okay. So here CPSID I. I means it will operate on the PRI mask register. D means it will turn off all the interrupts. Okay, D stands for disable. Okay, it will turn off all the interrupts by setting the PRI mask register. Okay, so it will turn on only reset NMI hard fault interrupts. All other interrupts will be disabled. Okay. Similarly, if I want to enable all the interrupts, means I am writing 0 into the PRI mask register. I am clearing the PRI mask register. I want to write into that register. I am clearing that PRI mask register. So I will use this E, that is enable. Okay, E stands for enable. CPSIE I. I means it will use PRI mask. D means disable. E means enable. Okay, I'll show you that here. Okay, I'll execute and show that. So CPSID I means CPSID I means it is PRI mask register. Now you are going to make this as 1. So it will disable all the interrupts. Okay, if I execute this, you can see that PRI mask is equal to 1. Okay, then if I execute CPSIE, I means it will clear the PRI mask register. Okay, PRI mask is equal to 0. It will enable all the interrupts. Here it will disable all the interrupts except reset NMI and hard fault. Is this clear? CPSID, CPSIE. Yes. Okay. So this is with respect to PRI mask. So similar to PRI mask here, Okay, we have another register called as the fault mask register. Okay, so what is the purpose of fault mask register? The purpose of the fault mask register is similar to PRI mask. Okay, so it is similar to PRI mask, but here, if you see the fault mask register, it is also a 1-bit register, right? It is also 1-bit register. So what it will do is, if we write 1 in this register, so what it will do is, it will enable only reset and NMI, non-maskable interrupts. You are doing very, very, very critical job. Okay, I don't want any disturbance, right? I will switch off this hard fault also. Okay, in that case, only reset NMI is enabled, turned on. All other interrupts, including hard fault, is turned off. All the different 90 interrupts are there, right? Everything is turned off. Only reset NMI is turned on. Okay, that is the function of this fault mask register. Okay, so what does this CPS instruction will do? CPSI, okay, what does this instruction will do is, here if we go, so we have this F here, CPSID F. So what does F stands for? Fault mask. Okay, it will set the fault mask register. When it sets the fault mask register, only reset NMI, these are turned on or active. Only these two interrupts are active. All other interrupts will be disabled. If we make this, see, if we use this instruction CPSID F, right? Understood? So if we use CPSI E means enable. You are going to enable the fault mask register here. That is, again, you are enabling or turning on or activating all the interrupts. D means you are deactivating or disabling all the interrupts except reset NMI. Only these two things will be enabled, right? So if you see here, CPSID F, if we use, you can see this fault mask register here. Okay, this is the fault mask register. So if we execute this, fault mask is equal to 1. Means it will disable all the interrupts except reset NMI. All other things will be disabled. Okay, then if we execute CPSIE-F, you can see this next instruction, CPSIE-F, means it will enable all the interrupts. Okay, you can see that it is enabling all the different interrupts here, right? So these are very, very important instructions. Okay, so normally you can do use any of these instructions, load, store, all those things, but these are very important instructions. That is MRS. Okay, that is move from special register to register. When we want to read the contents of uh, the special registers, like what are the special registers? If we come here, these things, MSP, link register, program counter, then program status register. All these different registers, if we want to access, we can access through this move from special register to register instruction. Okay, you can read those register contents through this move from uh, special register to register. Okay, we are moving in this instruction the application program register contents into one of the general purpose registers or not, right? Then the next step is like I want to write into the uh, whatever special function register. How to write into that register? Whatever you want to load, load it in one of the general purpose registers and transfer that to the special purpose register. These instructions are very important, and this CPSID, CPSIE with I and F is very, very important, right? These things we will be using uh, more in our programs. Okay, there are various other instructions also in the assembly level language instructions here. Okay, this also we will be using branch instruction. This is an unconditional branch instructions, right? Branch, whatever label you give here, it will go to that particular label. Okay, for example, yeah, I will add one more program. Branch is not there here. This. Okay, you can see here, okay, branch greater than. This is the label. What it will do, I'll just remove this greater than. If I give branch to loop means after this instruction, it will go to this label loop. Okay, this is the branch instruction, right? So this is whatever, if we just use B, it is a unconditional branch, just like go to statement. Okay, next is here BL. Okay, what is this BL? Branch with link register. Okay, so branch with link register to label. Okay, so here if we go to this, okay, so all the instructions cause a branch to label or to the address indicated in the RM. Okay, means what it will do is that is wherever whatever address we provide in the link register, okay, it will go to that, use that address and it will go to that particular instruction, right? Next, we have the BLX, means branch indirect with link register, right? Here we provide the address in the link register and whatever register is there, and it will branch to that. Is a register that indicates the address to the branch. Okay, so BLX RM, BX RM. Okay, these two things, it will directly jump to the label. These two things, we have to provide the address in RM. These are all the branch instructions. Okay, so with these branch instructions, we can provide the conditions, that is branch greater than, branch less than, right? Like that, you can branch less than or equal to, branch if equal to, right? Branch if not equal to, it will check the zero flag and If zero flag is not equal to 1, it will branch. Okay, branch equal to means it will check the zero flag. If zero flag equal to 0, then it will branch, right? Like that, based on various flags, we have the different branch instructions. Okay, so like this, various assembly language instructions are available. Okay, this will take a very long time to cover all these different instructions. Just you should know the overview of these instructions. Okay, what are the different assembly language instructions? Very important things you should know. Okay, when anything you want to use, you can just come to this manual and you can see and use those instructions. Okay, you have compare instructions, like this, different instructions. This is XOR operation. This is if then. This is load multiple, store multiplier, left shift operand, right shift. Okay, logical shift right, right? Multiply and accumulate MLA, multiply and subtract MLS, right? Like this, various or instruction, logical or not instruction, various instructions, push, pop. Okay, these two things also we will be using the push and pop when we access the stack. Okay, so with the push, whatever registers list you give, those register contents will be pushed to the stack memory. So when you are using pop means whatever registers you give, the depending on those many registers, the contents of the stack will be popped into these registers. You can get the values in these registers. Whereas here you are pushing the values into the stack, whatever register values you want, right? Push and pop instructions are there, right? These are the various very important instructions in the assembly language here. Okay, this also is very important. If you are waiting for some interrupt, you can give WFI. Okay, this also will be used most of the time. When you are waiting for any event to occur, wait for event, WFE, that is also very important, right? These are the very important instructions available, right? So next, what we will do is uh, writing these assembly level language programs. Now it is not recommended, right? We have very good assemblers uh, which will convert, or good compilers which will convert the high level language programs into the assembly level language programs. We have lot of compilers, assemblers. Assemblers will convert from assembly to machine level language. Compilers will convert from the high level language to the machine level. Intermediate step, it will convert to assembly level also, right? That's what we see when we go to this debug. Right, all these instructions, we go to the disassembly window, we can see the assembly language instructions, right? So but to access those core registers and all, still uh, one or two very important assembly language instructions we will be using in C or C++ languages to access these different core registers, or to access the hardware. We don't have a ready-made C instruction for that. In that case, while you write the firmware, you are going to use only very few assembly language instructions at a very critical task, right? So how do we, you are writing, this is a very this is one of the assembly language programs what we have written here. Uh, Here, I'll go to this here. This particular instruction, this particular program, we are going to add all the numbers in this array. Okay, so we have defined these many numbers. We are going to add all these different numbers, right? This assembly language is unique to the STM32 microcontroller, what we have chosen as the target, right? Whatever target we have chosen, depending, this program runs on that particular target. Okay, so I cannot use this STM32 program with the Infineon programs. It has different assembly language programs. Suppose if you are changing the controller or the processor after a period of time, but still the application is on, then you need to migrate this code to that particular processor. It's a again scratching from the starting from the scratch if you are doing this assembly language programming, because that assembly language is completely different, right? So we write this C language programs, right? Whatever program we write, it will be in C or C++ or Java or MicroPython. So many embedded programming languages are there. We write the programs in that, right? So when you write these programs, how do you insert these assembly language instructions into the C program, into the high level language program, right? That's our next topic. Okay, how do we write a C program with the assembly language instructions? Okay, to write the C program with the assembly level language instructions, here we have the GCC compiler. Okay, so this GCC compiler has an inline assembly code here. Okay, so how do we use this? Inline assembly code is used to write the pure assembly code inside a C program. Okay, I can write a pure assembly code, that is move R naught comma R1, right? So this is the assembly instruction. This is the pure assembly instruction. So how do I write into the C language? I have to use this inline assembly statement, underscore underscore ASM, then volatile. Okay, this inline statement should be written. So how do I do that? I will just remove these two files. I'll add a C file here. Yeah, just see. Yeah, here. Okay, so let it be here only. Just open, which has, yeah. Okay, like this, you can use underscore underscore ASM volatile. Inside the double quotes, you can insert any of the assembly level language instructions, right? So this is the format. Okay, so then uh, yeah, okay. I'll remove these things. I'll keep only this. Okay. Underscore underscore ASM, I can insert any assembly level language statement here. See, for example, underscore underscore ASM, I'll put. Then volatile keyword, we know what is its usage in the C language, right? I can use any instruction like move or not, comma, ash 1 2 3 4 H, like that. 0x 1 2 3 4. Okay, so something like this, right? So I will compile this file and show you the output. Okay, so if I come to this first instruction, this is underscore underscore ASM volatile. What you're doing, you're moving the data 1 2 3 4 into the register or not. Okay, so yeah, you can see 1 2 3 4. When you execute this instruction, you will get 1 2 3 4. Right? 1 2 3 4 is moved into or not. Like this. This is a pure C program, what we have executed. Right? In that, we have inserted this assembly language statement. Right? So the next step here is, uh, yeah, this is a very simple assembly language statement, right? It does not involve any variables in the C or any memory. It is just with the core registers only you are using, right? You can use any assembly language instructions here, right? So when you want like this also you can write, like each instruction one by one also you can write, or with one underscore underscore ASM volatile you can write multiple assembly statements also in this way. Okay, this can also be done, right? So uh, these are the two formats which you can follow. If only one instruction you want to add into the C, then you can use this single, or if you want to insert multiple assembly level language statements, you can use this format instead of writing underscore underscore ASM volatile every time, right? These two formats can be followed. Okay. Next step, these instructions, they are just within the core register contents only. Okay. So what if there is a C variable declared? Okay. We have the C variables here. For example, int variable 2. Okay. When you declare this int variable 2, what will happen? Inside the memory, there will be, since this is a local variable, it will be memory is allocated to this variable inside the stack, right? Memory is allocated into this variable for this variable in the stack memory, since it is uh, a local or automatic variable, right? So its value is 78. Right? Now, I want this, whatever is the C variable, I want to move it into the one of the registers R1. So how do I do that? How do I combine the C variables with the core registers? Right? Are you understanding my point? C variables into the registers. Okay, variable 2 into this register or not. How do I do that? Okay, so these things, how do we do that? Right? For that, we have the inline assembly format. This is the general form of the inline assembly statement. We have always inline assembly statement should start with underscore underscore ASM volatile, right? And then we have the first parameter as the code. What is this code? Code is nothing but the pure assembly language statement. In these things, whatever examples we saw, we have just the uh, pure assembly statement, which is inside the CPU only with the CPU registers. This is nothing but our code, right? Next is the C variables here. Output operand list, input operand list. Means output operand list means a list of output operands separated by commas. Okay. So, for example, if your C variable is a output variable, okay, means I am writing into this variable from the register. Okay, I want to move, for example, I want to move the contents of register or not to the variable 2. Then that variable 2 comes here. If we are writing into the variable, C variable, this is the operand list. What variable we want to write? Right? That is the output operand list. Next, we have the input operand list. Input operand list means you are reading the data from the variable into the register. For example, I have variable 2, which has 65. That 65 need to be loaded into some or not. That is our input operand list. Okay, output is for writing the data into the C variable. Okay, you're writing the data from the C, writing the data to a C variable. You're writing the data to the C variable from the core register. Okay, or not R1, any general purpose register. Whereas input operand means you are reading. You are reading the C variable value into register, into the general purpose register. Okay, if I want to represent this, if this is the register here and this is the C variable. So here what you are doing is from the register to the variable you are writing. Okay, input operand list is if this is the register and this is the variable, then what you are doing is you are reading from the variable into the register. This is the input operand list. Okay, so next we have the cobbler list. We will see this later. Okay, so this is the general format. Let us take, for example, here this is the output operand list here. Okay, this is the code. Okay. Okay. This is the general format of inline assembly statement. Okay. Till now, is it clear about the inline assembly statement? Okay, can I use MSR to write 0 or 1 to the PRI mask? Yes, you can do that. Okay, you can do that. Uh, it involves two assembly statements, right? Move or not or 1 with 0 or 1, and then you have to use this MSR instruction, right? Two instructions are required. Uh, so instead of that, you can just use one instruction with CPS. Okay. So till now, is it clear? Okay. Yeah. Now, see, I have a call at 12:45 to 1 p.m. There is one call. I will share you. I'll share you some videos or some this thing. Yeah. Okay. So let me see what is there here. Yeah. Yeah. Okay. I'll share you this video. I'll just complete that meeting and come back. Yeah, it's an important one. I'll come back on this. Till then, you go through this video. Will it be okay? You can be in the meeting. We will complete this. Tomorrow onwards, we can start with the GPIO or embedded C programs. Okay? Yes? Is this available? Can you check? Okay.
Hey,
Yeah, I'll
welcome
go
back.
attend the
Let's
meeting
do
and
this
come back.
example. To the
Be in the meeting itself. We will come back and continue on this. Okay, at 1 o'clock. Okay. Yeah. Please try these examples. Okay. You have the Keel software installed, right? Whatever examples he's telling, you can just create a C program like this in the Keel software. Any C program. Okay. So here one C program is there. You can with int, just like you write a C program, you can write and execute and see. Okay, just give me 15 minutes. We will come and continue. Okay. Yeah. Okay, then we'll meet at 1 o'clock. Okay. Yeah.
content of control register to C variable control reg. Here, control register is a special register of the ARM core. How do you read the special register, which is control register? To read a special register, there are some separate instructions in the instruction set. Let's explore that. In order to explore all the instructions of your processor, you have to refer to the instruction